The mystery of the interstellar visitor, now called 3I, Atlas continues to grow with every passing week, as new observations reveal a world that has crossed unimaginable gulfs of space to wander, for a brief moment, through our inner solar system, a place utterly unlike the deep dark between the stars, and yet, for a short while, this object now gliding toward its closest brush with Earth is allowing astronomers to watch its story unfold in real time and to ask what happens when ancient frozen matter forged beyond our sun is suddenly plunged into intense light and heat like a long, silent traveller stepping into a floodlight of energy and physics. For this discussion, imagine that we are sitting together as colleagues in a quiet lecture hall, the lights dimmed as images of this strange body fill the screen, and the aim is not drama for its own sake, but a clear, precise understanding. You are old enough and professional enough to appreciate the numbers, the geometry, and the sequence of events, yet still close enough to student life, that curiosity is sharp and questions come quickly. This tone will remain as the story deepens through later parts, because what begins here with dates and distances will soon expand into chemistry, magnetic fields, and the possibility that such objects might carry the raw ingredients for life between the stars. The video that frames this investigation sets a clear promise. At the outset, it will provide a full breakdown of what is currently known about 3I Atlas, based on direct observation, careful measurement, and comparisons with other small bodies and meteorite samples. There is no need for speculation dressed as certainty. Instead, every step is grounded in data that can be checked. Light curves, spectra, images, and orbital calculations, all tied together to draw out a coherent physical story. This structure will hold across all later parts, so that each new layer of interpretation connects back to firm observational anchors already laid down rather than floating loose as disconnected guesswork to orient ourselves in time and space. We begin with the key dates that define this encounter. 3. Atlas reached its closest approach to Earth on December 19th, passing our planet at a safe distance but close enough that even modest observatories could join the watch and help build up a continuous record of its behaviour. Long before that moment, the recording that guides this narration was made on December 3rd, when the object was already bright, active and well placed for study. Between those two dates, astronomers knew that changes could occur day by day, small shifts in brightness or structure in its tails that might hint at internal processes. Still adjusting to the fierce radiation of the inner solar system. Another critical moment came even earlier, on October 29th, when 3I Atlas passed through perihelion, its closest point to the Sun along its current orbit. This is the point in its path where solar radiation is strongest, where light and charged particles pour onto its surface with maximum intensity. At perihelion, the object received more energy in a short span than it would have experienced over enormous stretches of its prior journey through deep space, and it is at or near this stage that shifting ices, sublimation gas jets, dust release, and internal restructuring often accelerate, transforming a quiet, icy body into an active cometary source with complex tails and evolving brightness patterns. To understand why perihelion is so important, consider the physics of solar radiation. The energy flux from the Sun drops rapidly with distance, so that an object cruising in the far outer reaches of a system experiences only a faint trickle of light. But as it moves inward, that trickle becomes a torrent. For 3, Atlas perihelion was the point of maximum solar power. Input, a turning point where previously stable ices and trapped gases could no longer remain inert under that bombardment surfaces. Fracture, Subsurface layers, warm and once slow chemical reactions suddenly race forward. You can think of it as a long frozen laboratory sample, abruptly thrust under a powerful lamp after ages in a freezer. The story, however, does not begin at perihelion but months earlier, with a more violent kind of solar interaction. Even before reaching its closest point to the Sun, 3I Atlas was struck by multiple solar storms, bursts of energetic particles and magnetic disturbances that propagate outward through the heliosphere with notable force. When one of these storms sweeps across an object, like 3I Atlas, it can alter the surrounding plasma environment, disturb charged dust, and potentially stimulate jets or localized outgassing. By depositing energy beneath the surface, repeated hits before perihelion mean that the object was not only slowly warming, but was also repeatedly jolted by sudden injections of solar energy and changing magnetic conditions, setting the stage for some of the anomalies and unusual activity that will be explored in later parts. Tracing the journey of 3I Atlas through our observational records requires stepping back to its first formal detection on July 1, when survey instruments finally picked out its faint motion against the background of seemingly fixed stars. These surveys continuously scan large areas of the sky, hunting for subtle changes that betray moving bodies. And in this case, the algorithms and observers flagged a source whose trajectory and speed did not match ordinary long-period comets of our own system. That initial notice was crucial because it allowed the astronomical community to begin rapid follow-up, refine the orbit, and recognize that this was not just another icy wanderer from the distant Oort cloud, but an object arriving from deep interstellar space, as is often the case with unusual discoveries. The story did not end with the first detection. Once the approximate orbit of 3I Atlas was known, astronomers turned back to older sky catalogue images, archived exposures taken months earlier for unrelated projects. By searching these images, they found that the object had already been recorded unknowingly as a faint moving dot. This process, sometimes called precovery, extended the observational arc backward in time, shrinking the uncertainties on the orbit and confirming that its path through space could not be bound to the Sun in any long-standing way. This careful reconstruction is what underpins the designation of 3I, identifying it as the third, recognized interstellar object known to pass through our solar system from the moment its unusual nature became clear. 3I Atlas was tracked almost continuously as it descended into the inner solar system. Telescopes across multiple longitudes and latitudes coordinated to follow its motion so that gaps caused by daylight or bad weather in one location could be filled by observations elsewhere. This dense coverage is not merely a matter of collecting pretty images, it allows scientists to build detailed light curves, map changes in colour and morphology, and track the development of tails jets and evolving structures around the nucleus by comparing subtle differences from night to night and week to week. Researchers can infer how fast materials are being lost, which areas of the surface are active, and whether internal processes, such as structural failure or cryovolcanic events, might be reshaping the object from within. By the time of the December 3 recording, all of these strands came together into a coherent early phase. Picture of 3I Atlas. We have an interstellar body, first recognized in July, whose presence was then traced backward in older data, its path calculated to reveal an approach that carried it into the deep gravitational well of our Sun. It endured repeated solar storms before experiencing maximum solar radiation at perihelion in late October, and through that time it was placed under near constant scrutiny as it progressed inward toward a mid-December flyby of Earth. Each of these milestones will connect directly to the later discussion of its chemistry, magnetism, and possible role as a carrier of organics across interstellar distances, which is why this first part concentrates so carefully on establishing the timeline and geometry of the encounter. Standing at this point in the narrative, it is useful to remember that 3I Atlas is not merely a curiosity, but a natural experiment, one that the universe is conducting for us willingly, or not an object that spent untold ages in the deep dark, is now being forced through a rapid energy transition, and we have the instruments and theoretical tools to watch what happens next. In part 2, this story will move outward from simple orbit and dates into the environmental contrast between deep interstellar space and the inner solar system, showing how that immense difference in energy exposure begins to explain the profound physical changes already hinted at in its light and activity, and laying the groundwork for the remarkable chemistry and cryovolcanic behavior that will emerge in the following parts. In the first part, we set the stage by following 3I Atlas from its initial detection in early July through its repeated encounters with solar storms, its intense perihelion passage on October 29, and its steady approach toward Earth, culminating in the mid-December flyby that allowed nearly continuous tracking of its changing appearance in this second part. We step back from that timeline to ask a deeper question. What kind of environment did this object inhabit before it ever came near our Sun? And how does that ancient context shape the transformations that are now being observed? To begin, imagine 3I Atlas in the great emptiness between stars far outside the influence of any single stellar system in that realm. The average energy exposure is extraordinarily low. There is no nearby star pouring light and heat onto its surface. Instead, the background glow is dominated by the faint combined light of distant stars, the cosmic microwave background, and a tenuous bath of particles drifting through the interstellar medium over millions or even hundreds of millions of years. An object there cools toward a deep equilibrium, its surface and interior, settling into a state that changes only slowly as chemical reactions and phase transitions grind along at glacial speeds. Low energy, however, does not mean complete safety, even in the most remote interstellar regions. 3I Atlas would still have been struck by galactic cosmic rays, high-energy charged particles accelerated by supernova remnants, active galactic nuclei and other violent astrophysical engines. These cosmic rays can punch through meters of material, disrupting molecular bonds and occasionally altering the atomic structure of minerals buried beneath the surface over vast timescales. Such radiation gradually modifies the outer layers of an object, darkening ices, altering organic compounds, and perhaps building up complex chemistry within protected pockets. But because the overall energy flux is low, most material remains frozen stable and unprocessed compared to what we see near a star. The contrast with the environment near our own Sun is stark. As 3I Atlas plunged inward, the solar energy flux at a distance comparable to the orbit of Earth reached roughly 735 watts per square meter, a concentrated stream of photons that dwarfs the diffuse glow of interstellar space. This is the kind of energy density that can drive rapid sublimation of volatile ices, fracture surface layers and power jets that fling gas and dust into space. Within a relatively short span of time, the object was forced to transition from a regime where change was slow and subtle to one where sunlight itself became an active geological and chemical agent, reshaping both its appearance and its internal structure. This immense energy difference is not a minor detail but a central physical driver. It creates a situation where major changes are not just possible but expected as previously stable ices. Within 3I Atlas begin to warm. They cross thresholds at which molecules can move more freely, bonds can break and reform, and trapped gases can escape through cracks and pores. The result is a complex evolution in which the outer layers may fracture and vent, while deeper regions start to respond more slowly, producing delayed reactions long after the initial heating peak. This is why monitoring over months rather than days is so important. The object does not simply flare once and settle. It undergoes an extended transformation driven by both direct heating and the slow propagation of that heat. Inward orbital analysis suggests that this dive toward our Sun represents the first close encounter with the star that 3I Atlas has experienced in at least 10 million years. Perhaps much longer. That estimate reflects the absence of any clear gravitational perturbations in its incoming trajectory that would betray a recent pass near another stellar system. Instead, its path appears smooth and undisturbed, consistent with an origin in the general galactic field, rather than from a tightly bound cluster where frequent stellar encounters are common for at least that span of time and likely longer. It seems to have wandered unmolested through the interstellar medium. Further investigations of its incoming direction hint that 3I Atlas has not passed particularly close to any known star within about 500 parsecs along its prior path. That distance range is large on human scales, but modest on galactic terms, and the lack of close approaches strengthens the case that this is a long duration interstellar traveller rather than a recent ejection from a nearby system. The implication is that whatever structure and composition it carries have been shaped by conditions that existed very early in its history and then preserved across enormous distances with only slow cumulative modifications from cosmic rays and sparse interstellar dust impacts. This history of long isolation is crucial for interpreting the multiple unexpected anomalies that observers began to report. As 3I Atlas neared the Sun, features in its light curve, changes in tail geometry, and signs of complex outgassing did not match simple models based on ordinary comets from our own Oort cloud. Those native bodies have typically made repeated passes through the inner solar system, each pass partially reworking their surfaces and selectively removing the most volatile materials. By contrast, an object like 3I Atlas that has never before undergone such extremes may still retain abundant primordial ices, exotic compounds, and fragile structures that respond in unfamiliar ways when suddenly exposed to strong stellar heating. For the first time, the evolution of 3I Atlas, as recorded from July through and beyond perihelion, therefore shows not just minor cosmetic changes but major shifts directly triggered by sunlight jets turning on or off, brightness jumping in ways that indicate new regions, becoming active, and structural rearrangements that hint at deeper internal reconfiguration. Each of these observable signatures points to specific physical processes, such as global cryovolcanic reactions or transitions between different ice phases that are being forced into action by the rapidly changing energy environment. The earlier parts of its life in the dark serve to preserve a complex internal inventory of volatiles and minerals, while this sudden encounter with the star is now unlocking that inventory piece by piece. It is important to emphasize that the time 3I Atlas has spent in deep space before arriving here remains fundamentally unknown. Orbital reconstruction can tell us where it has been over the last few million years or so, but not precisely when it was first ejected from its original system or how long it drifted through the galaxy before its path intersected our solar neighborhood. That unknown span might be tens of millions of years, or even far longer, during which the object would have silently orbited the galactic center, experiencing only the slow accumulation of radiation damage and minor impacts, yet retaining the basic structure and composition imprinted during its formation and early evolution. This vast unmeasured history is part of what makes 3i Atlas such a valuable natural sample. When all of these OAs are put together, a coherent physical picture emerges. 3i Atlas is an ancient interstellar body, forged in a distant environment and then left for immense periods in a low-energy, deep freeze, occasionally nudged by galactic tides and distant stellar passages, but never strongly reworked. Only now has it been thrust into the intense light and wind of a star like our Sun, where it is undergoing a rapid and observable transformation. The anomalies seen in its activity are not signs of something unnatural, but of natural processes unfolding in a context that we have rarely had the chance to study directly, an essentially pristine object, meeting a stellar furnace for the first time as we move into the next part of this narrative. The focus will narrow from the broad environmental contrast between interstellar space and stellar proximity to the specific manifestations of that transformation in the visible structure of 3i Atlas itself, in particular the development of a surprising sunward-facing tail, the shrinking of the traditional anti-sun tail, and the abrupt brightness changes that first signaled a deep internal shift. These visible features will become the first strong evidence that the energy jump described here has ignited large-scale cryovolcanic behavior within the object, marking a new phase in its evolution that can illuminate both its composition and its long journey through the galaxy. In the first part, the focus was on establishing the journey of 3i Atlas from its first detection in July through repeated solar storms past its intense perihelion passage and toward its close approach to Earth, while the second part stepped back to contrast the cold quiet of a deep interstellar space with the harsh, bright environment near the Sun, showing how that energy jump set the stage for dramatic physical change. Now, in this third part, the attention turns to what telescopes actually began to see as that energy took hold: a strange rearrangement of tails, a sudden persistent brightening, and the first clear signs that the object was not merely venting gas, but undergoing a fundamental internal transformation. Most comets develop a familiar geometry as they near the Sun. The material streaming away from the nucleus tends to form an anti-sunward tail, pushed backward by radiation pressure and the solar wind. But in the case of 3i Atlas observers began to report an unexpected feature: a distinct sunward-facing tail, a structure pointing toward the Sun rather than away from it. This kind of morphology can arise when relatively heavy dust grains or charged particles are guided by local magnetic and plasma conditions, so that material is effectively drawn or confined toward the direction of the star instead of being swept cleanly outward. The emergence of such a sunward feature immediately signaled that something more complex than a textbook comet tail was unfolding around this interstellar body. At the same time, the more familiar anti-sun tail did not simply grow stronger with decreasing distance as might have been expected. Instead, that tail began to shrink and dim, even as overall activity continued in other forms. Its fading suggested that the supply of easily lifted, fine dust or certain volatile gases feeding that particular structure was being altered, perhaps depleted or redirected by changing internal pathways or by the newly developing sunward flows, rather than a simple monotonic increase in a single tail. 3i Atlas was clearly reorganizing the way it expelled material into the surrounding space, a sign that internal pressure sources and surface vents were shifting as the heating pattern evolved. The sunward tail, by contrast, grew larger and brighter, with time indicating that more material was being channeled into that unusual configuration as the object approached the Sun and then passed through perihelion. This growth implies that processes on or beneath the surface were not static but intensifying in a way that favoured emissions that could be shaped into a sunward jet or dust structure, perhaps because of changing thermal gradients or newly opened conduits. The net result was a kind of morphological inversion, the canonical bright anti-sunward tail weakening, while this striking sunward component became the dominant visible signature of activity. While imaging revealed these geometric changes, spectroscopic observations provided early chemical clues. Narrow slices of the spectrum taken from light reflected and emitted by 3I Atlas showed patterns characteristic of specific molecules and dust components. These data confirmed that the object was expelling gases and particulates in combinations that pointed toward a rich inventory of volatiles and minerals, some of which match those seen in dark outer solar system bodies and primitive meteorites. But the precise balances and line strengths did not map perfectly onto familiar templates. This mismatch hinted that 3I Atlas contained a mixture shaped by interstellar history rather than by repeated close passages near our Sun, and it set the stage for interpreting later evidence of magnetite formation and organic-rich chemistry. A key moment in understanding that something extraordinary was happening came when the light curve revealed a sudden brightness increase at around 2.5 astronomical units from the Sun. Long before perihelion, at that distance, solar heating is strong enough to begin sublimating water ice in a global way, rather than only affecting the most volatile ices at isolated patches. As 3I Atlas crossed this threshold, its brightness jumped by roughly 2 magnitudes, meaning it became about 6 times brighter than before. Such a jump cannot be explained by a simple smooth increase in reflected sunlight. It requires a major rise in the amount of dust and gas being thrown into space. What made this brightening even more significant was that after the event, the brightness did not fall back to the previous trend line. Instead, the object maintained a higher baseline output, suggesting that a new mode of activity had been triggered, perhaps a global reorganization of vents or the onset of large-scale cryovolcanism, as the inner regions crossed the temperature threshold for water-assisted eruptions. That the light curve did not simply spike and then relax, but instead held at an elevated level, tells us that whatever changed at around 2.5 astronomical units represented a durable alteration in the internal state of 3I Atlas as the object continued inward toward perihelion. The rate of brightening accelerated rather than following a gentle, predictable curve, typical of a modest comet. This acceleration indicates that additional regions were becoming active, or that existing active areas were expanding and deepening their output. The combination of increasing insulation and the earlier disruption at 2.5 astronomical units likely allowed heat to penetrate further into the nucleus, unlocking previously isolated reservoirs of volatile material. Once these deeper layers began to respond, the overall dust and gas production rose faster than simple surface heating alone would predict, pointing to a more global interior response taken together. The appearance of a strong sunward-facing tail, the dimming anti-sun tail, the persistent brightness, jump at 2.5 astronomical units, and the accelerated brightening into perihelion all point toward a major internal transformation rather than a mere superficial shedding of frost. A plausible explanation is that internal ices and trapped gases reached pressures and temperatures that triggered widespread cryovolcanic behavior, where subsurface pockets of volatile, rich material heated by the advancing thermal wave erupted through fractures to the surface, releasing gas and entrained particles in powerful vents. Such eruptions can naturally give rise to complex tail geometries and sustained high activity, as long as the internal reservoirs remain pressurized and warm. It is this constellation of evidence that provides the first strong observational support for cryovolcanic behavior. In 3I Atlas, the object is not just passively evaporating in sunlight, but undergoing internally driven events that reshape its emission patterns and perhaps even its mechanical structure. That this happens when an interstellar object is exposed to stellar heating. For what appears to be the first time in many millions of years, makes the case even more compelling. Energy deposited by the sun is not only sculpting the outer coma, but is also reconfiguring the interior, converting a long frozen interstellar relic into an active, evolving world. Before our instruments, as the narrative continues, the next part will dive more deeply into the physical and chemical consequences of this cryovolcanic activity, focusing on the formation of magnetite minerals, the emergence of magnetic field characteristics, and the role of the surrounding plasma in shaping both the tails and the protective environment around 3I Atlas themes that connect directly back to the unusual morphology and light curve changes described here, and that will eventually tie into larger questions about organic chemistry and the possibility of life-seeding material travelling between the stars. Up to this point, we have followed 3I Atlas, from its discovery and first approach through its emergence from the deep freeze of interstellar space and into the intense domain of the sun, watching as a sudden brightening at around 2.5 astronomical units and the growth of a powerful sunward tail signaled that something profound was happening inside this object. The simple picture of a quiet, icy fragment slowly evaporating in sunlight is no longer enough. Instead, all the evidence points toward a world that has been forced into a new active state, its interior awakening as ancient ices cross critical thresholds and begin to drive large-scale cryovolcanic eruptions that reshape its surface and surroundings. The key physical process at the heart of this awakening is cryovolcanism, the transition of ices directly from solid to vapor, under heating and pressure, rather than the red-hot lava of terrestrial volcanoes. Here the erupting material is predominantly volatile ice that flashes into gas carrying dust and fragments with it as it escapes from fractures and vents on the surface. In the case of 3I Atlas, this means that subsurface reservoirs of water, rich and carbon-bearing ices that remained stable for millions of years in deep space are now being mobilized by the advancing thermal wave from the sun. As those layers warm, they begin to sublimate, driving gas upward until it finds or forces pathways through the crust. Once these channels open, the gas escapes explosively or in sustained jets, generating the complex coma and tails that observers have recorded. Cryovolcanic outflow is not composed of pure transparent gas alone. It carries with it tiny grains and larger particles of rock and metal stripped from the internal matrix of the object. Among these materials, evidence points toward the formation of magnetite minerals, iron oxide phases that arise when water interacts with iron-bearing metals. Under suitable conditions, the presence of both water and metallic components within 3I Atlas creates a natural setting for such reactions as cryovolcanic processes, cycle liquid or superheated water through cracks and pores contacting fresh metal surfaces. Those corrosion reactions convert part of the metal into magnetite, locking water. Derived oxygen into solid form while releasing hydrogen and helping to reshape the internal chemistry over time. Magnetite is not only a chemical product, it also carries a distinct physical property. It can become strongly magnetized and respond to ambient magnetic fields under the right conditions. Fine grains of magnetite dispersed through the dust and rock of 3I Atlas contribute to its overall ability to interact with magnetic fields both intrinsic and external, as these grains are lofted by cryovolcanic jets and embedded within the surrounding coma. They help to create regions where charged particles move differently and where magnetic stresses can organize material into filaments or arcs. This is one reason why the behavior of the tails and visible structures around the object is so closely tied to the magnetic and plasma environment near the Sun as cryovolcanism continues. And more magnetite-rich dust is released, 3I Atlas begins to exhibit detectable magnetic field characteristics, even if it does not possess a traditional internal dynamo, like a large planet. The combination of magnetizable minerals and flowing plasma can generate effective magnetic signatures, localized regions where field lines are distorted and where charged particles are guided along specific paths in practice. This means that the space immediately around the object becomes structured by invisible magnetic scaffolding that shapes the coma and tail in ways that can deviate significantly from the simple picture of neutral gas freely expanding into a vacuum. The unusual sunward tail described earlier is very likely one visible imprint of this magnetically influenced environment. Surrounding all of this is the solar wind, a continuous flow of charged particles streaming outward from the Sun, which together with the embedded interplanetary magnetic field creates a dynamic plasma environment through which 3I Atlas must travel as the object outgasses. It does not release neutral material into empty space alone. The gases quickly become ionized by ultraviolet light and collisions, producing a plasma cloud around the nucleus. When the solar wind encounters this cloud, it is slowed, deflected, and sometimes compressed, forming structures analogous to miniature bow shocks and magnetospheres. Here, the newly created magnetite dust grains and other conductive particles can enhance these effects, strengthening local fields and intensifying the interaction between the solar wind and the object. This interplay between intrinsic mineral magnetism and the external plasma environment adds layers of complexity to the observed behavior of 3I Atlas, the shifting shapes of its tails, the appearance of filaments and jets, and the way activity seems to respond to solar storms are not random. Instead, they reflect a constantly evolving balance between outgassing rates, dust production, plasma density, and magnetic field geometry. As solar storms sweep past increasing particle flux and altering field direction, they can temporarily strengthen or distort the miniature magnetic structures around the object, enhancing shielding in some regions while opening new channels for charged particles elsewhere. This dynamic can in turn feed back into the cryovolcanic processes by altering how energy is deposited on and near the surface. To interpret these phenomena, scientists draw heavily on comparisons with other icy and primitive bodies where in situ or sample-based data exist. Even though 3I Atlas is unique in its interstellar origin, it can be analysed alongside comets from our own Oort cloud, outer solar system, moons with cryovolcanic activity, and meteorites that preserve records of water-rock reactions. In their mineralogy, Such comparative studies show that when water interacts with iron and nickel-bearing material under low-temperature conditions, magnetite and related minerals form reliably, that organic compounds, including complex carbon chains, and even simple sugars and amino acids can be synthesized or preserved within these environments, and that repeated cryovolcanic cycling can concentrate and redistribute such materials near the surface, where they become accessible to observation or sampling on bodies. Where direct sampling has been possible, organic compounds have indeed been documented alongside water and mineral phases, similar to those inferred for 3I Atlas analyses of carbon-rich meteorites and dust returned from comets reveal the presence of water, bound within minerals as well as free or trapped in ices, together with a diverse suite of organic molecules, ranging from simple hydrocarbons to more complex structures, including sugars, amino acids, and related species. These findings support the idea that 3I Atlas is not an inert rock, but very likely an organic, rich body whose interior has hosted the slow chemistry of water, rock, and carbon for immense periods before being reactivated by solar heating. The new information gained from monitoring 3I Atlas has therefore dramatically improved our understanding of what interstellar objects can be, rather than mere frozen stones drifting between the stars. They can be chemically active. Laboratories combining cryovolcanism, water-driven mineral alteration, magnetite formation, and organic chemistry into a single evolving system, the emergence of magnetically structured tails, the response to solar storms, and the strong signs of water-related mineralogy all point in the same direction. This object is both a witness to ancient interstellar conditions and an active participant in present-day solar physics, its behavior stitching together disciplines that usually remain separate from planetary geology to plasma physics and astrobiology. With these foundations in place, the next part of the narrative will turn to a more precise classification of 3I Atlas through its spectral traits, its similarity to D-type outer solar system bodies, and its connection to extremely rare carbonaceous meteorites that carry water and organics in abundance by tying its visible and chemical signatures to these known samples. Researchers can anchor this interstellar visitor within a broader family of primitive materials and begin to infer where and how such an object might have formed, long before it began its lonely voyage across the galaxy, having traced the journey of 3I Atlas through its discovery, its violent activation at around 2.5 astronomical units, and the onset of large-scale cryovolcanism that released magnetite bearing dust and structured its tails around magnetic and plasma fields. The natural next step is to determine what kind of object this is, where it might have formed, and what its composition tells us about the distant system that once held it. Before it was flung out into the interstellar void, spectroscopy and photometry provide the key clues here, because the colour and spectral signatures of an object reveal the chemical composition of its surface and the outgassed materials, allowing astronomers to match 3I Atlas to families of known bodies and meteorites that share similar traits among the classification schemes used for small solar system bodies. One important distinction is made between D-type objects and B-type objects. Both groups are dark, but D-type bodies are characterized by particularly steep red spectral slopes and very low reflectivity, or albedo, meaning that they absorb most of the sunlight that hits them and appear dark even when relatively close to the sun. The reddish colour comes from complex organic compounds and carbon-rich materials that have been irradiated or chemically processed over long timescales, forming darkened crusts enriched in organic molecules relative to fresh rocky or icy surfaces. These spectral traits point directly to higher concentrations of organics than are found in other asteroid types such as the brighter, less red B type asteroids. Observations of 3I Atlas show that its spectrum matches the spectral traits of D-type objects closely. It exhibits the same dark, featureless red-sloped signature that indicates abundant organics and carbon-bearing minerals mixed with anhydrous silicates. This match is not superficial because the spectral slope and lack of strong absorption features at visible and near-infrared wavelengths are diagnostic of surfaces where organic compounds dominate over silicates or metals. The similarity to D-type asteroids found in the outer main belt and among the Jupiter Trojans tells us that 3I Atlas very likely formed in a cold, distant region where volatile ices and carbon-rich materials could accumulate and remain preserved, suggesting an origin environment far from the heat of its parent star, much like the outer regions of our own solar system. The connection between 3I Atlas and D-type asteroids becomes even more compelling when we look at meteorite samples that are believed to come from D-type parent bodies. The Tagish Lake meteorite, which fell to Earth in the year 2000, is considered to be the most primitive of the carbonaceous chondrites and is often linked to D-type asteroids based on spectral and compositional matching. It belongs to a rare subgroup known as CR, carbonaceous chondrites, which are distinguished by their high content of water bound in minerals and their abundance of organic molecules, including amino acids, simple sugars, and complex carbon chains. That Tagish Lake and related CR samples are extremely rare in meteorite collections underscores just how special and fragile these materials are. They represent some of the most ancient and least altered matter from the early solar system. CR carbonaceous chondrites are rich in both water and organics, with water making up several percent of their mass locked into mineral structures such as serpentine and other hydrated silicates. Alongside this water are diverse organic compounds ranging from simple hydrocarbons to more complex molecules that include functional groups containing oxygen, nitrogen, and sulfur. The preservation of these volatile, rich phases tells us that CR meteorites and their parent bodies never experience significant heating beyond about 200 degrees Celsius after their formation, meaning they retain a nearly pristine record of the chemical conditions in the outer protoplanetary disk, where ices, volatiles, and carbon compounds were abundant, and where temperatures remained cold enough to prevent thermal destruction of delicate organics. What makes the CR connection particularly important for understanding 3I Atlas is that these meteorites are thought to have formed outside the main planet-forming disk in the cold, distant regions beyond where the giant planets assembled, where water ice, carbon dioxide ice, and organic-rich grains condensed onto growing bodies. This formation zone lies beyond what is called the carbon dioxide snow line. The distance from a young star where carbon dioxide can freeze into solid particles along with water ice and other volatile objects that accreted in this region would naturally incorporate large amounts of ice and organics into their interiors, producing bodies with compositions very similar to what is inferred for 3I Atlas and for D-type asteroids in our own system. The spectral and compositional similarities between 3I Atlas D-type asteroids and CR chondrites together suggest a similar origin for the interstellar visitor. It likely formed in the outer reaches of a protoplanetary disk around another star, where conditions allowed volatiles and organics to survive and accumulate. Once formed, these bodies represent ancient, untouched material reservoirs of the primordial chemistry that existed in the disk before planets fully assembled, because they accreted far from the central star and were never subjected to intense heating or repeated close passes through warm inner regions. Their interiors preserve a frozen snapshot of early disk conditions, including the mix of water ice, organic molecules, and metal grains that would later drive the cryovolcanic and magnetic behavior seen as 3I Atlas entered our solar system. Additional evidence for this interpretation comes from the observed volatiles escaping from 3I Atlas as it nears the Sun. Spectroscopic data show the presence of carbon monoxide, carbon dioxide, and water vapor in ratios that point to a strongly oxidized chemistry, consistent with materials that formed in a water-rich oxygen-rich environment similar to what is inferred for carbonaceous chondrite parent bodies. The detection of these molecules alongside the magnetite dust and the red organic rich surface crust all converge on a picture of an object that is fundamentally similar in composition to the most primitive meteorites we have sampled directly, reinforcing the idea that 3I Atlas is carrying material that has remained largely unaltered since the epoch of planetary system formation in its home system alongside water and simple gases. The presence of iron and nickel in notable amounts is confirmed both through the magnetite formation discussed earlier and through dust grain analysis. These metals are common in primitive bodies, and when present together with water and carbon compounds, they enable a suite of chemical reactions that can produce organics and other complex molecules. That 3I Atlas contains both the raw ingredients, water, organics, metals, and the energy source solar heating. To drive reactions makes it a natural laboratory for studying how interstellar matter evolves when exposed to stellar environments, and how such bodies might contribute to the delivery of organic rich material to planets in other systems or even back to systems they pass through. Taken together, the spectral match to D-type objects, the compositional parallels with CR carbonaceous chondrites, the evidence for formation outside the main planet-forming disk, and the preservation of ancient untouched volatiles and organics all point to a coherent origin story. For 3I Atlas, it is very likely a fragment or small body that formed in the cold outer regions of a distant protoplanetary disk. Billions of years ago, was later ejected by gravitational interactions with giant planets or stellar encounters, and has since travelled through interstellar space, carrying within it a frozen record of the chemistry and conditions that prevailed in that ancient disk, now exposed to the Sun for what may be the first time in millions of years. It is revealing that record through its cryovolcanic outbursts, magnetite production, and organic-rich emissions, bridging the gap between meteorite science and the study of interstellar objects. As the narrative moves forward into the next part, the focus will shift to the specific chemistry that drives the formation of magnetite and the release of carbon monoxide and carbon dioxide, examining the elevated nickel to iron ratio, the role of water-metal corrosion reactions, and how these processes naturally explain the magnetic behaviors and gas production observed, without requiring any exotic or artificial mechanisms. This chemical perspective will deepen the connection between 3I Atlas and primitive solar system materials, while also setting the stage for later discussion of amino acids, organic evolution, and the possibility that such objects could seed life-bearing chemistry across the galaxy. In the previous part, we established that 3I Atlas closely matches the spectral characteristics of D-type asteroids and the composition of CR carbonaceous chondrites, pointing to an origin in the cold outer regions of a distant protoplanetary disk where water, ice, and organic compounds accumulated into pristine bodies that have remained largely unaltered over billions of years. Now the discussion turns to the specific chemistry unfolding within and around this object, as solar heating activates reactions between water, ice, and metal grains, driving the formation of magnetite and releasing carbon-bearing gases, while also revealing an unusual nickel to iron ratio that holds clues to both the organic chemistry and the magnetic properties observed in the evolving coma and tails. One of the key findings from spectroscopic analysis and dust modelling is that 3I Atlas exhibits an elevated nickel to iron ratio compared to what is typically seen in ordinary rocky bodies or most common meteorite types in carbonaceous chondrites and primitive outer solar system materials. Nickel is often present alongside iron in metal grains at concentrations several times higher than in more processed materials. This elevated ratio is significant because nickel plays a catalytic role in certain organic producing reactions, particularly those involving carbon monoxide and hydrogen under appropriate conditions. Nickel-rich surfaces can facilitate the synthesis of simple organic molecules through processes similar to the Fischer-Tropsch reaction used industrially to convert carbon monoxide and hydrogen into hydrocarbons, meaning that the elevated nickel content in 3I Atlas is not merely a passive compositional detail but an active chemical enabler. The presence of both water and metals within the interior of 3I Atlas sets the stage for corrosion reactions that are well understood in laboratory studies and observed in meteorite samples. When liquid water, or even high-temperature water vapour, comes into contact with metallic iron and nickel, the metals oxidize, transferring electrons to the water molecules. This reaction produces iron oxide minerals such as magnetite while releasing hydrogen gas as a byproduct. The hydrogen can then participate in further reactions with carbon-bearing molecules, or it can escape into space, contributing to the observed outgassing, the formation of magnetite. Through these water-metal interactions is not speculative, but a well-documented process in both terrestrial weathering and in the alteration history recorded in carbonaceous meteorites, where magnetite grains are commonly found embedded in hydrated mineral matrices. Magnetite itself is known for possessing strong natural magnetism. It is one of the few minerals that can retain a permanent magnetic field or become magnetized in the presence of an external field. Fine grains of magnetite suspended in dust or embedded in larger fragments therefore contribute directly to the magnetic properties of the material being expelled from 3I Atlas as cryovolcanic vents eject dust clouds. Rich in these grains, the surrounding space becomes populated with magnetizable particles that can organize along magnetic field lines, enhance local field strengths, and create complex structures in the tails and coma. This is why the unusual sunward tail and filament patterns discussed earlier are not just geometrical curiosities, but are direct physical consequences of the magnetite-enriched dust interacting with the solar wind and the interplanetary magnetic field. The key driver for all these transformations is exposure to the sun as 3I Atlas moved from the cold interstellar medium into the intense radiation environment. Near our star, the temperature of its outer layers began to rise, crossing thresholds where water ice transitions from solid to vapour and where chemical reaction rates accelerate. Dramatically, solar heating does not act uniformly across the surface but creates thermal gradients, hot sunlit regions and cooler shadowed areas that can set up internal circulation of gases and liquids. These thermal gradients can drive subsurface water through fractures, bringing it into contact with fresh metal grains and initiating the corrosion reactions. The previous part established that 3I Atlas contains an elevated nickel to iron ratio, and that water-metal corrosion reactions driven by solar heating naturally produce magnetite carbon monoxide and carbon dioxide, while also releasing hydrogen that can participate in further chemistry. Now the focus shifts to the organic dimension of this chemistry, examining how nickel-based catalysis can efficiently produce organic compounds, how similar primitive bodies have yielded amino acids and sugar-related molecules, and how the dark red surface of 3I Atlas itself is very likely the product of billions of years of organic accumulation and radiation processing. In the depths of interstellar space, these connections will deepen the case that this object is not merely a frozen rock, but a travelling repository of prebiotic chemistry. Nickel-based chemistry is known to be highly efficient at producing organic molecules from simple starting materials such as carbon monoxide, hydrogen, and water vapour. In industrial settings, nickel catalysts are used to drive reactions that convert mixtures of carbon monoxide and hydrogen into hydrocarbons and alcohols through mechanisms that build carbon chains. Step by step, the same fundamental processes can occur naturally on the surfaces of nickel-rich metal grains within carbonaceous bodies, where gas phase molecules adsorb onto the metal, react, and then desorb as more complex organics over millions of years. Even slow reaction rates can build up significant inventories of organic compounds, especially when the body remains cold enough to prevent decomposition, and when fresh reactants are continuously supplied by sublimating ices or delivered by impacts. Evidence from meteorite and sample return missions shows that similar objects in our own solar system contain a remarkably diverse suite of organic molecules. The Murchison meteorite. A well-studied carbonaceous chondrite contains more than 70 different amino acids, including many not used by life on Earth, as well as sugars, nucleobases, and complex aromatic hydrocarbons. More recently, samples returned from the asteroid Ryugu by the Hayabusa 2 mission revealed amino acids and other organics preserved within grains that had experienced aqueous alteration, similar to the processes inferred for 3I Atlas. These findings demonstrate that primitive water-rich bodies naturally accumulate and preserve organic chemistry, and that the presence of amino acids and glucose-related compounds is not exotic, but expected in objects that formed in cold organic-rich environments and underwent water-rock interactions. The dark red surface of 3I Atlas is itself a strong indicator of organic enrichment. When mixtures of simple ices, such as water, methane, ammonia, and carbon monoxide, are exposed to ultraviolet light or cosmic ray radiation, over long periods they undergo photochemical and radiolytic processing that creates complex organic residues known as tholins. These materials are typically dark reddish or brownish in colour and have broad featureless spectra that absorb strongly across visible and near-infrared wavelengths. Exactly the kind of signature observed in the spectra of 3I Atlas and D-type asteroids. The colour and spectral slope are therefore not just aesthetic features but direct evidence that the surface has been chemically modified by radiation during its long journey through interstellar space, building up a crust of irradiated organics. This kind of dark red organic crust is also seen on trans-Neptunian objects, small icy bodies that orbit far beyond Neptune in the cold outer reaches of our own solar system. These objects share many characteristics with 3I Atlas, including low temperatures, organic rich compositions, and surfaces processed by cosmic rays and solar wind particles over billions of years. The spectral similarity between 3I Atlas and trans-Neptunian objects strengthens the interpretation that both populations formed under similar conditions in cold, distant regions of protoplanetary disks, and that both have retained primordial organic inventories. The main difference is that trans-Neptunian objects have remained in orbit around the Sun, while 3I Atlas was ejected from its birth system and spent untold time wandering the galaxy before arriving here. The organic surface crust likely formed during the long phase of space travel when 3I Atlas was isolated far from any star in that environment. The only significant energy sources were galactic cosmic rays and occasional impacts from interstellar dust. Grains, cosmic rays, are high-energy particles that can penetrate meters into a body, ionizing and breaking chemical bonds. Along their paths, when these particles strike ices and simple organics, they trigger reactions that build more complex molecules layer by layer over millions of years. This slow, steady processing gradually darkens and reddens the surface, while also creating a chemically diverse mixture of organic compounds that range from simple hydrocarbons to amino acids and more complex nitrogen and oxygen-bearing species. The result is a surface that is both a record of and a product of its interstellar voyage. Organic materials accumulated over billions of years do not remain static. They can continue to evolve chemically, even in the absence of strong external energy inputs, through processes such as polymerization, molecular rearrangement, and low-temperature, solid-state reactions. However, these processes are generally very slow and become effectively frozen when temperatures drop below a few tens of degrees above absolute zero, as would be the case in deep interstellar space only when the object is reheated, such as during the current passage near the Sun, do reaction rates accelerate, allowing previously dormant chemistry to resume. This reactivation can drive the formation of new organic species, the release of volatile organics into the coma, and further modification of the surface layers as solar ultraviolet light and heat interact with the organic crust. The presence of water in different physical states, depending on location within 3I Atlas, adds another layer of complexity to the organic chemistry near the surface where temperatures have risen above the sublimation point of water ice. The released water vapor can interact with organics, either catalyzing new reactions or carrying dissolved organic molecules into gas phase deeper within the nucleus where temperatures remain. Lower water may still exist as ice or, in localized pockets, as liquid, if pressure and salts or other impurities depress the freezing point. Liquid water is a particularly effective solvent and reaction medium. It can mobilize organic molecules, facilitate their interaction, and promote the formation of more complex structures, including amino acids and simple peptides. This means that as 3I Atlas warms, some regions may host transient liquid water zones, where organic chemistry can proceed much more rapidly than in solid ice. Many amino acids have indeed been found on similar bodies, both in meteorites and in samples from asteroids. These include glycine, alanine, and a variety of other species that are fundamental building blocks of proteins in terrestrial biology. The detection of amino acids in such diverse settings shows that they form readily under a wide range of conditions wherever carbon, nitrogen, oxygen, hydrogen, and liquid or gas phase water are present together. Amino acids are not unique to life but are common products of prebiotic chemistry. That 3I Atlas shares compositional and spectral traits with bodies known to contain amino acids strongly suggests that it too harbours these molecules within its organic rich interior. A higher concentration of amino acids and other complex organics is expected in less processed objects, those that have never been heated significantly or exposed to repeated cycles of evaporation and redeposition. In this regard, 3. I-Atlas is an ideal candidate because its long isolation in interstellar space followed by a first encounter with a star means that it has avoided the kind of thermal cycling that ordinary comets undergo, with each perihelion passage preserving a more pristine inventory of organics. This preservation makes it particularly valuable for studying the original organic content of protoplanetary disk materials and for understanding how such chemistry might be delivered intact to planets in other systems or even back to the system of origin if the object were ever to return. As 3I Atlas continues to approach and then move away from the Sun, its organic chemistry can evolve further. The combination of solar heating, ultraviolet radiation, and the presence of water and catalytic minerals creates an active environment where new molecules can form, existing ones can break down, and complex mixtures can redistribute between gas-solid and possibly liquid phases. This ongoing evolution means that observations made at different times during the encounter can capture snapshots of organic chemistry in progress, revealing how prebiotic molecules respond to stellar environments, and whether such processes can enrich the surrounding space with organic rich dust and gas that might eventually be incorporated into other bodies such as planets or moons. The idea that space travel over billions of years could build up complex molecular layers on the surface and within the interior of an interstellar object is well supported by laboratory experiments and theoretical models. When ice mixtures are irradiated under controlled conditions, they produce the same kinds of dark organic residues seen on 3I Atlas and similar bodies. Scaling these results to cosmic timescales shows that even low doses of radiation can accumulate into significant chemical change. Given enough time, the surface of 3I Atlas is therefore not just a passive layer but an active archive of chemical history, recording the cumulative effects of radiation, cosmic ray exposure, and perhaps even interactions with interstellar gas and dust along its journey. With this understanding of organic chemistry in place, the next part will turn to the broader implications of these findings, exploring whether 3I Atlas might be classified as a life-seeding object, examining the water to carbon dioxide and carbon monoxide ratios that reveal its oxidation state, and considering the possibility that Earth could intersect its perihelion trail in the coming months, potentially allowing us to sample particles released during its closest approach to the Sun. These themes will connect the detailed chemistry described here to larger questions about the role of interstellar objects in distributing organic materials across the galaxy and seeding planetary systems with the raw ingredients for life. The previous part demonstrated that nickel-based chemistry on 3I Atlas can efficiently produce organic molecules that amino acids and glucose compounds have been found on similar primitive bodies, and that the dark red surface formed through billions of years of radiation processing in interstellar space, building up complex organic layers. Now the discussion turns to a provocative but scientifically grounded question: whether this object might be classified as a life-seeding carrier, examining the water and carbon gas ratios that reveal its chemical state, and considering the tantalizing possibility that Earth may soon pass through the trail of particles expelled during its perihelion, allowing direct sampling of material from this ancient interstellar traveller. The concept of a life-seeding object refers to a body that carries the essential ingredients for life: water, organic molecules, and perhaps catalytic minerals across interstellar distances, and delivers them to planetary systems where conditions might allow biology to take hold. This idea is not science fiction but a recognized hypothesis within astrobiology known as panspermia, or more specifically, lithopanspermia, when applied to rocks and ices rather than living organisms themselves. Given that 3I Atlas contains abundant water, as confirmed through spectroscopic detection of water vapor in its coma, along with organic compounds, metals and minerals, it fits the profile of such a carrier. Whether it could actually seed life depends on whether those materials survive. The journey remain accessible and are delivered to environments where they can participate in prebiotic chemistry. Water has been confirmed on 3I Atlas through multiple lines of evidence, including the direct detection of water emission lines in spectra, taken as the object outgasses, and through the inference of water-driven cryovolcanism that best explains the sudden brightening and sustained activity. Discussed in earlier parts, the presence of water is not marginal, but substantial enough to drive large-scale sublimation and to have participated in the aqueous alteration reactions that formed magnetite and hydrated minerals within the interior. This water is not merely trapped ice, but an active participant in ongoing chemistry, capable of dissolving, transporting and concentrating organic molecules and minerals as the object warms. The relative abundances of water, carbon dioxide and carbon monoxide, provide important constraints on the chemical history and oxidation state of 3I Atlas. Measurements indicate that the carbon dioxide to water ratio is around 8:1, meaning that for every molecule of water detected, roughly 8 molecules of carbon dioxide are observed. This high ratio suggests that carbon dioxide is a major volatile component, possibly more abundant than water in the actively sublimating layers, or that it is released preferentially at the temperatures and locations currently active on the object. Carbon dioxide abundance is typical of bodies that formed in cold oxidizing environments where carbon could combine with oxygen rather than remaining as elemental carbon or forming reduced species like methane. Similarly, the carbon monoxide to water ratio is around 1.65, indicating that carbon monoxide is also present in significant amounts, though somewhat less abundant than carbon dioxide. Relative to water, the presence of both carbon monoxide and carbon dioxide alongside water points to a strongly oxidized chemistry, one in which oxygen has been incorporated into multiple phases, including ices, minerals, and gas species. This oxidation state is consistent with formation in the outer regions of a protoplanetary disk, where water ice, carbon dioxide, ice, and carbon monoxide, ice, could all condense, and where subsequent aqueous alteration further oxidized metals and carbon-bearing materials. The ratios measured are therefore snapshots of ancient disk chemistry preserved through interstellar travel and now being revealed as the object heats despite the dominance of oxidized carbon gases. 3I Atlas still retains significant amounts of water and metals, including the nickel and iron discussed earlier. This combination is critical because it means the object has not been completely processed or outgassed. It still harbours reservoirs of volatile and reactive materials that can participate in chemistry, both internally and in the surrounding coma. The presence of metals alongside water and organics is particularly important for catalytic processes that can synthesize more complex molecules, and for generating magnetic fields through magnetite formation, linking back to the magnetic behaviors and organic production. Described in previous parts, the overall composition of 3I Atlas, as inferred from gas ratios, dust properties and spectral signatures closely matches that of organic-rich meteorites, particularly the Cr carbonaceous chondrites, which are known to contain amino acids, sugars, and other prebiotic molecules in abundance. This match supports the interpretation that 3I Atlas is not a barren rock, but a chemically rich body with a high likelihood of harbouring amino acids and other organic building blocks in concentrations comparable to or exceeding those found in the most primitive meteorites that have fallen to Earth. If samples from this object could be analysed directly, they would very likely reveal a complex organic inventory spanning simple hydrocarbons to amino acids and possibly even more complex structures. One of the most exciting prospects raised by the current encounter is the possibility that Earth will cross the perihelion trail of 3I Atlas in the months of March through April as the object rounds the Sun and heads outward. It sheds dust and gas along its orbit, creating a debris stream that spreads out along the orbital path over time. If Earth's orbit intersects this trail, our planet could encounter particles released during the perihelion passage when activity was at its peak and when the most material was being expelled into space. Such particles would enter the atmosphere as meteors, and some fraction, particularly the smaller grains, might survive entry and settle to the surface, where they could be collected and analysed. The potential for direct sampling of 3I Atlas material through meteor collection is scientifically invaluable because it would provide the first opportunity to study interstellar object composition at the molecular and isotopic level in a laboratory. Rather than relying solely on remote spectroscopy, researchers could measure isotope ratios that reveal the object's formation, environment, identify specific organic molecules, and their chirality or handedness, analyze mineral structures and magnetic properties, and compare all of these traits directly with meteorite samples and returned asteroid material. If particles from 3I Atlas are indeed recovered, they would represent a sample of another star system's planetary material delivered to Earth naturally, without the need for an expensive interstellar sample return mission. The idea that 3I Atlas could release particles into regions that Earth will pass through is supported by the observed outgassing and dust production as the object approached perihelion and continues to move away. Its coma and tails spread material over a wide area, along and perpendicular to its trajectory. The solar wind and radiation pressure push smaller particles outward and along curved paths, while larger grains follow trajectories closer to the original orbit over weeks and months. This material disperses, forming a tenuous cloud that extends for millions of kilometers. If the geometry is favorable, Earth's passage through this region in spring could result in detectable meteor activity, or at least in the collection of dust particles by high-altitude aircraft or stratospheric balloon missions already designed to capture interplanetary and interstellar dust. The composition of any recovered particles would test the predictions made from remote observations if they contain abundant organics, hydrated minerals, magnetite, and elevated nickel to iron ratios. It would confirm the interpretations laid out across these parts and validate the techniques used to characterize interstellar objects. From a distance, conversely, any surprises in the chemistry or mineralogy would refine our understanding of how such bodies form and evolve. The particles themselves might carry isotopic signatures distinct from solar system materials, marking them as definitively extrasolar in origin and providing clues to the nucleosynthetic history of their parent star and disk. Beyond the immediate scientific return, The possibility of sampling 3I Atlas material connects to broader questions about how organic rich interstellar objects might contribute to the chemical evolution of planetary systems if such objects regularly pass through stellar systems and shed material along the way. They could act as vectors for organic delivery seeding planets and moons with prebiotic molecules that might otherwise take much longer to synthesize locally. In this sense, 3I Atlas and bodies like it are not merely passive wanderers but active participants in galactic chemistry, redistributing the products of stellar nucleosynthesis and disk chemistry across vast distances and potentially influencing the conditions under which life can emerge on distant worlds. With the chemical ratios, organic content, and potential for Earth-based sampling now established, the narrative will move forward. In the next part, to examine the future trajectory of 3I Atlas, including its close approach to Jupiter in mid-March and its eventual exit from the solar system, while also addressing how the observed chemistry aligns with natural oxidation processes and requires no artificial or exotic explanations. This will set the stage for discussing the detailed light curve and the specific event at 2.5 astronomical units that marks the beginning of global cryovolcanic transformation. The previous part explored the possibility that 3I Atlas might function as a life-seeding object carrying water, organics and metals across interstellar space, and examined the chemical ratios that reveal its strongly oxidized state, while also raising the tantalizing prospect that Earth could intersect its debris trail in the coming months, allowing direct sampling of particles released during perihelion. Now the focus shifts to the future trajectory of this interstellar visitor, its upcoming close approach to Jupiter, and its eventual departure from our solar system, while also addressing how all the observed chemistry aligns perfectly with natural processes, requiring no exotic or artificial mechanisms to explain the composition, activity, or evolution of this remarkable body after its closest approach to Earth on December 1903. I-Atlas will continue along its hyperbolic trajectory outward through the solar system, but before it escapes entirely, it will make one more notable gravitational encounter. In mid-March, it will pass relatively close to Jupiter, the largest planet in our system. This flyby will not capture the object or significantly alter its path because its velocity relative to the Sun is too high for Jupiter's gravity to bind it into an orbit, but the encounter will provide another opportunity for observation as ground-based and space-based telescopes track how the object responds to Jupiter's intense radiation belts, magnetic field, and gravitational influence. If any changes in activity or tail structure occur during that passage, they could reveal additional details about the object's internal state and its sensitivity to external forces following the Jupiter encounter. 3I Atlas will continue outward, crossing the orbits of Saturn, Uranus, and Neptune over the following months and years, gradually returning to the low-energy environment of interstellar space from which it came throughout this outward journey. It will be tracked as long as its brightness remains detectable, and as long as observatories can allocate time to follow it. The outbound leg is scientifically valuable because it allows researchers to monitor how the object's activity declines as solar heating decreases, whether any delayed outgassing or structural changes occur, and how the coma and tails fade and eventually disappear as the object cools and distances itself from the Sun's influence. This long-term monitoring will complete the observational arc, providing a full picture of how an interstellar body responds to passage through a stellar system. Comparing 3I Atlas to rare meteorite types has proven essential for understanding its composition and history. The match to CR, carbonaceous chondrites and the spectral resemblance to D-type asteroids together. Anchor this object within a framework of known primitive materials. Even though it originated in another star system, the chemistry it displays is not alien in the sense of being fundamentally different from what we see in the most ancient unprocessed bodies in our own solar system. Instead, it reflects universal processes of disk formation, ice condensation, aqueous alteration, and organic synthesis that operate wherever planets and small bodies form around stars. This universality is reassuring because it means the tools and concepts developed from studying meteorites and solar system objects can be applied confidently to interstellar visitors. The chemistry observed in 3I Atlas aligns closely with natural oxidation processes that occur when water, metal, and carbon-bearing materials interact over long timescales. In cold environments, the formation of magnetite from iron and nickel through water-driven corrosion, the production of carbon dioxide and carbon monoxide from the oxidation of carbon and organic compounds, and the generation of hydrogen as a byproduct are all well-documented reactions in laboratory experiments and in the geological records of carbonaceous chondrites. There is no need to invoke unusual energy sources or non-standard chemistry to explain these observations. They follow directly from the initial composition of the object and the environmental conditions it has experienced first during its formation and aqueous alteration in a protoplanetary disk, and now during its reactivation by solar heating. The nickel-to-iron ratio elevated, relative to more thermally processed bodies, is also expected from early formed objects that accreted in the outer regions of a disk and never underwent significant heating or differentiation in such environments. Metals condense with their primordial proportions, and any subsequent aqueous alteration preferentially oxidizes iron over nickel because iron is more reactive. This leaves behind metal grains enriched in nickel relative to the original bulk composition. The elevated ratio is therefore a natural marker of primitive undifferentiated material that has experienced water-rock interaction rather than an anomaly requiring special explanation. This same pattern is seen in the least altered carbonaceous chondrites, reinforcing the connection between 3I Atlas and known primitive solar system samples. Solar heating is the primary driver of the volatile activation and cryovolcanic behavior seen in 3I Atlas as the object moved from the frigid conditions of deep space into the intense radiation field near the Sun. Its surface and subsurface layers warmed, triggering the sublimation of ices, the pressurization of trapped gases, and the eventual breaching of surface barriers that allowed material to escape this sequence of thermal activation, sublimation, pressurization, and eruption is exactly what is expected from models of comet activity and has been observed repeatedly in short-period and long-period comets from our own Oort cloud. The difference with 3I Atlas is that it is undergoing this process for what appears to be the first time in millions of years, making the response more dramatic and revealing previously untapped reservoirs of volatiles and organics. No artificial source or intervention is required to explain the composition, activity or evolution of 3I Atlas. Every feature from its dark red organic-rich surface to its magnetite, bearing dust to its complex tail, morphology and sustained brightening can be accounted for by natural astrophysical and geochemical processes. This point is worth emphasizing because the unusual nature of interstellar objects and their rarity can sometimes lead to speculation about non-natural origins. But in the case of 3I Atlas, the full body of evidence points unambiguously to a natural small body formed in the outer regions of a distant protoplanetary disk ejected into interstellar space through gravitational interactions, and now temporarily visiting our solar system, where it is being heated and transformed by our Sun in ways that are dramatic but entirely consistent with known physics and chemistry. The long-term evolution of 3I Atlas will remain observable for months or even years, depending on telescope sensitivity and the object's intrinsic brightness as it moves outward. The combination of decreasing solar flux and increasing distance will cause its activity to wane. The coma will shrink, the tails will fade, and eventually the object will return to a dormant state, indistinguishable from the cold, inert body it was before entering our solar system. However, the material it has released will continue to spread along its orbit and disperse into the surrounding space. Some of that material may remain gravitationally bound to the Sun, eventually contributing to the zodiacal dust cloud or settling onto planets and moons, while other particles will escape entirely, joining the population of interstellar dust grains that drift between the stars. The observations accumulated during the inbound and outbound phases of this encounter fit the expected behavior of an interstellar object passing through a stellar system. The light curve shows a brightening phase, as solar heating increases a peak near perihelion, and a subsequent decline as the object moves away. The tail morphology responds to changes in solar wind conditions and plasma density. The spectroscopic signatures reveal gases and dust consistent with primitive carbonaceous compositions, and the overall activity level correlates with distance from the Sun in a way that matches theoretical predictions for cryovolcanic bodies. All of these patterns confirm that 3I Atlas is behaving as a natural icy object should when exposed to stellar heating, validating the physical models used to interpret its behavior and providing a benchmark for future studies of interstellar visitors. With the trajectory, chemistry, and natural origin of 3I Atlas firmly established, the narrative now turns in the next part to a detailed examination of the light curve itself, focusing on the major event that occurred at around 2.5 astronomical units from the Sun, when the brightness suddenly jumped and did not return to its previous baseline. This event marks the likely onset of large-scale water sublimation and global cryovolcanic reaction, a turning point in the object's evolution that connects all the earlier discussions of chemistry, magnetism and organic content into a single coherent physical story anchored by precise photometric measurements and a clear timeline of thermal and chemical transformation. In the previous part, we traced the future trajectory of 3I Atlas from its close Earth approach through its upcoming Jupiter encounter and eventual exit from the solar system, while confirming that all observed chemistry aligns with natural oxidation processes and requires no exotic explanations. Now the discussion narrows to one of the most critical pieces of evidence in the entire story: the detailed light curve of 3I Atlas and the major brightness event that occurred at approximately 2.5 astronomical units from the Sun. This event serves as a clear marker of a fundamental transformation within the object and provides the key to understanding how solar heating triggered a global cryovolcanic reaction that reshaped its activity and set the stage for all the subsequent observations of tail's magnetism and organic release. A light curve is a plot of an object's brightness over time, and for comets and other small bodies it serves as a diagnostic tool that reveals how activity levels change in response to external conditions, such as solar heating, and internal processes, such as sublimation and outgassing for 3I Atlas. Continuous monitoring from multiple observatories around the world produced a high-quality light curve that spans from its first detection in July through perihelion in late October and beyond into December. This curve shows not a smooth, gradual change, but a series of distinct phases, with the most striking feature being a sudden jump in brightness that began around early September, when the object was near 2.5 astronomical units from the Sun. The brightening event began around September 5 through 7, with observers reporting a rapid increase in the object's visual and photometric magnitude. Over just a few days, the magnitude increased by approximately 2, which in the logarithmic magnitude scale corresponds to roughly a 6-fold increase in brightness. This is not a subtle shift, but a dramatic change that cannot be attributed to improved observing conditions or a chance alignment. Instead, it signals a major increase in the amount of sunlight being reflected and scattered by dust and gas released from the nucleus, meaning that the rate of material ejection from 3I Atlas suddenly accelerated by a large or within a short time window. What makes this brightening particularly significant is that it persisted through perihelion and beyond, rather than spiking briefly and then falling back to the previous trend. The light curve shows that after the initial jump, the object maintained an elevated brightness level and continued to brighten further as it approached perihelion. This sustained increase indicates that the event at 2.5 astronomical units was not a transient flare, but the onset of a new mode of activity, one in which deeper or more extensive regions of the nucleus became active and continued to supply gas and dust at higher rates than before. The object had effectively shifted from a low activity state to a high activity state, and did not revert now as 3I Atlas moves away from the Sun, following its perihelion passage. The light curve shows a slow dimming consistent with decreasing solar heating and the gradual decline of outgassing as surface temperatures drop and subsurface thermal waves dissipate. This dimming phase is the expected counterpart to the brightening phase and confirms that activity is primarily controlled by solar distance and temperature. However, that the object remains significantly brighter than it was before. The 2.5 astronomical unit event shows that internal changes triggered at that distance continue to influence its behavior, even as it recedes outward, suggesting that structural modifications such as opened vents or exposed fresh ice maintain elevated activity levels. The distance of 2.5 astronomical units is highly significant in the physics of cometary activity because it corresponds roughly to the heliocentric distance at which water ice can begin to sublimate efficiently on a sunlit surface closer to the Sun than this threshold. Water ice transitions from a relatively stable solid to a vapor at rates high enough to drive noticeable outgassing and dust ejection farther out than 2.5 astronomical units. Water sublimation is too slow to dominate the activity, and more volatile ices, such as carbon monoxide or carbon dioxide, which sublimate at lower temperatures, are the main drivers of any observed gas release. The sudden brightening at this distance therefore points directly to water sublimation as the triggering mechanism at 2.5 astronomical units. The energy flux from the Sun is strong enough to raise surface temperatures above roughly 190 degrees Kelvin, the approximate temperature at which water ice sublimates at a rate sufficient to generate significant gas pressure and lift dust grains from the surface. But temperature alone is not the only, or if subsurface layers are porous or fractured, the advancing thermal wave can penetrate deeper warming ice below the surface and creating pockets of pressurized vapor that eventually break through the overlying crust. When this breakthrough occurs, it can be sudden and violent, resembling an eruption, and it can open new pathways that allow continuous outgassing from previously isolated reservoirs. This is the hallmark of cryovolcanic activity, driven not by molten rock, but by sublimating and possibly melting ice. The possibility of liquid water existing at or near 2.5 astronomical units may seem surprising, given that water is typically thought of as either solid ice or vapour in space. However, under certain conditions, liquid water can be stable or metastable for brief periods if subsurface pressure from overlying material or from trapped gases is sufficient. It can raise the boiling point of water, allowing it to remain liquid even at temperatures below the normal freezing point in vacuum. Additionally, the presence of salts, ammonia, or other antifreeze compounds dissolved in the water can depress the freezing point, allowing liquid brine to exist at temperatures well below 0 degrees Celsius. Laboratory experiments and observations of icy moons in our solar system, such as Europa and Enceladus, confirm that such conditions are physically plausible. If transient liquid water did exist within 3I Atlas at around 2.5 astronomical units, it would have profound implications for the chemistry occurring inside the object. Liquid water is an excellent solvent and reaction medium. It can dissolve salts and organics, mobilize ions, and facilitate reactions that are extremely slow or impossible in solid ice. The interaction of liquid water with metal grains would accelerate the corrosion reactions that produce magnetite hydrogen and oxidized carbon species, while also providing a pathway for organic molecules to concentrate and react with one another. In this scenario, the brightening event marks not just the onset of water sublimation, but the activation of a global aqueous chemistry system that had been dormant for millions of years. The interpretation of a global cryovolcanic reaction at 2.5 astronomical units ties together multiple strands of evidence. The light curve shows a sustained brightness increase. Beginning at that distance, spectroscopy reveals water vapour as a major component of the outgassing. The presence of magnetite in the dust indicates water-metal reactions have occurred, and the overall activity level suggests that large internal reservoirs of volatiles have been tapped rather than just surface frost being heated. This convergence supports the conclusion that 3I Atlas underwent a major internal transformation, crossing a thermal and chemical threshold that unlocked processes dormant since its formation in a distant protoplanetary disk. The chemical processes that produce magnetite and organics are directly linked to the availability of liquid or vapor phase, water and metals. As discussed in earlier parts, when water contacts iron and nickel grains, it oxidizes the metals, forming magnetite and releasing hydrogen. The hydrogen can then participate in reduction reactions with carbon monoxide or carbon dioxide, facilitated by nickel catalysts to produce organic molecules. This suite of reactions is thermodynamically favoured under the conditions inferred for the interior of 3I Atlas, and the energy input from solar heating provides the activation energy needed to drive these processes at observable rates. The result is a body that is simultaneously a cryovolcanic source, a mineralory, and an organic chemistry laboratory, all operating in real time as it passes through the inner solar system. The long period of space travel that preceded this encounter allowed 3I Atlas to accumulate and preserve the necessary starting materials for these reactions during its millions of years. In the cold of interstellar space, cosmic rays and interstellar dust impacts gradually processed its surface, building up organic layers and creating radiation-damaged minerals, but the bulk interior remained frozen and chemically inert, preserving primordial ices, metals, and simple organics. Only when solar heating penetrated deep enough to reach these reservoirs did the chemistry restart, with the sudden release of energy and material observed in the light curve, the object's long dormancy followed by rapid reactivation, makes it an ideal natural experiment in how ancient materials respond to stellar environments after extended isolation, with the critical brightening event at 2.5 astronomical units, now firmly established as the onset of global cryovolcanic activity, driven by water sublimation and accompanied by magnetite formation and organic chemistry. The narrative will move forward in the next part to explore the possibility that life, or at least prebiotic chemistry, could form on such an object, examining how magnetic protection supports the survival of complex molecules, how radiation can damage or create organics, and how 3I Atlas might function as a long-term carrier of organic materials capable of transporting them intact across interstellar distances and potentially delivering them to planets in other systems. The previous part demonstrated that the sudden brightening of 3I Atlas at 2.5 astronomical units marked the onset of large-scale water sublimation and global cryovolcanic activity, creating conditions where liquid water metal grains and organic compounds could interact, driving magnetite formation, hydrogen release, and organic synthesis. Now the discussion takes a bold step forward to address one of the most profound questions raised by this interstellar encounter: whether the conditions within and around 3I Atlas might permit not just the preservation of prebiotic molecules, but the actual formation of life, or at least the assembly of increasingly complex organic structures that approach the threshold of biological chemistry. This requires examining how magnetic protection supports molecular survival, how radiation can both damage and catalyze organic reactions, and how such an object might serve as a protected vessel carrying fragile chemistry across the galaxy. The possibility of life forming on an object like 3I Atlas is acknowledged by researchers not as a certainty but as a scientifically viable hypothesis, worth serious consideration. The key requirements for life, as we understand it, are liquid water, a source of organic molecules and energy to drive chemical reactions, and some form of protection from destructive radiation that would otherwise break down complex molecules faster than they can form. We have already established that 3I Atlas contains water in multiple phases, organics distributed throughout its interior and energy input from solar heating. The remaining question is whether it can provide sufficient protection from the harsh radiation environment of space to allow delicate chemistry to proceed and accumulate over long timescales. Magnetic protection plays a crucial role in supporting the survival of complex molecules in space-charged particles such as cosmic rays, and solar wind protons carry enormous energy, and when they strike organic molecules they can ionize bonds, break molecular backbones, and destroy the very structures that are essential for biochemistry, without some form of shielding. These particles would sterilize any exposed surface or shallow subsurface layer, preventing the buildup of amino acid sugars or more elaborate compounds. However, if a magnetic field can deflect or slow incoming charged particles, it creates a sheltered region where radiation doses are reduced, and where organic chemistry can proceed with less interruption. This is exactly the kind of protection that planetary magnetic fields provide for life on Earth, and it is the principle that may operate on a smaller scale around bodies. Like 3I Atlas, radiation without protection causes molecular damage through ionization and bond-breaking high-energy particles colliding with organic molecules. knock electrons out of their orbits, creating reactive radicals that can trigger chain reactions of decomposition over time. This leads to the breakdown of complex structures into simpler fragments and eventually into small volatile molecules that escape into space. Laboratory experiments show that amino acids, sugars, and other prebiotic compounds exposed to unshielded cosmic ray fluxes degrade on timescales of millions of years or less in interstellar space. This sets a limit on how long such molecules can survive unless they are buried deep within a body or protected by some other mechanism, such as a magnetic barrier that reduces the effective radiation dose. Comets are known to produce magnetic barriers through interactions between their outgassing plasma and the solar wind as a comet releases gas into space. The gas becomes ionized by ultraviolet light and collisions, forming a cloud of charged particles around the nucleus. When the solar wind encounters this plasma cloud, it is slowed and deflected, forming a structure called a bow shock and compressing the interplanetary magnetic field into a draped configuration around the comet. This draped field acts as a partial shield, reducing the flux of energetic particles that can reach the nucleus and near-surface regions. The more active the comet, the stronger the plasma cloud, and the more effective the magnetic shielding. This effect has been directly measured by spacecraft that have flown through cometary magnetospheres, such as the Rosetta mission to Comet Churyumov-Gerasimenko. The strength of this magnetic barrier increases during solar storms, when the solar wind density and magnetic field intensity rise sharply. The enhanced plasma pressure compresses the magnetic field around the comet more tightly, creating a stronger shield that can deflect even higher energy particles. Conversely, during quiet solar conditions, the shielding weakens, allowing more radiation to penetrate. This variability means that the level of protection experienced by organic molecules within or near a comet fluctuates over time, but on average, active comets maintain a degree of shielding that is significantly better than passive bodies with no outgassing. The That-3i Atlas has been highly active since crossing 2.5 astronomical units, suggests that it is currently producing a substantial plasma cloud and associated magnetic barrier. Given its cryovolcanic activity and the presence of magnetite-bearing dust, it is highly likely that 3i Atlas has developed a similar magnetic protection system. The magnetite grains enhance the local magnetic field by becoming magnetized in the ambient interplanetary field and by contributing to the overall magnetic structure of the coma. When combined with the ionized gas released by sublimation and cryovolcanic vents, this creates a complex magnetic environment that can trap, deflect, or slow charge particles, reducing the radiation dose experienced by material in the inner coma and near-surface layers. This shielding would be strongest during periods of high activity and near perihelion, when outgassing rates and solar wind interaction are most intense. This magnetic and plasma shielding supports the potential preservation of organic compounds within the coma and on or near the surface of 3i Atlas. Even though the object is exposed to solar, ultraviolet light and solar wind particles, the combination of magnetic deflection and the buffering effect of the dense coma can reduce the effective radiation environment by orders of magnitude compared to unprotected interstellar space. This means that amino acids, sugars, and other prebiotic molecules released from the interior during cryovolcanic eruptions have a chance to survive in the coma for extended periods, rather than being immediately destroyed, allowing them to be transported away from the nucleus and potentially delivered to other environments such as planetary atmospheres or surfaces. If the object passes close enough, the idea that an object like 3I Atlas could behave as a carrier through space, transporting organic materials across interstellar distances, relies on this combination of internal protection through burial in ice and external protection through magnetic and plasma shielding. During interstellar travel, the interior remains cold and shielded by overlying layers, reducing radiation damage to manageable levels over millions of years upon entering a stellar system and activating through solar heating. The object generates a magnetic environment that continues to protect the newly released organics as they are expelled into space. This dual-layer protection burial during transit and shielding during activity makes such objects plausible vectors for delivering complex organic chemistry to planets that might otherwise lack sufficient raw materials for the origin of life. The potential for long-term transport of materials across star systems depends critically on the ability of interstellar objects to survive the journey without being completely degraded by cosmic rays, interstellar dust, impacts, or internal radioactive decay. 3I Atlas has clearly survived such a journey intact, arriving at our solar system with abundant volatiles, organics and reactive metals still present. This demonstrates that preservation over millions of years is not only possible but likely common among interstellar bodies of this type, that it is now actively releasing those materials in a relatively protected magnetic environment suggests that the chemistry it carries could be delivered to other bodies in a form that remains chemically useful rather than being reduced to inert carbon and simple gases. Whether life could actually originate on an object like 3I Atlas rather than merely being transported by it remains speculative, but the ingredients are present: water in liquid and vapor forms, organic molecules, including likely amino acids and sugars, energy from solar heating and chemical reactions, and a degree of radiation protection from magnetic fields. The main limitation is time. The object spends only a brief period, months to years, in the warm inner regions of a stellar system where liquid water and active chemistry are possible, before returning to the cold of interstellar space. This short window may be insufficient for the complex processes of polymerization, self-organization, and natural selection that characterize the origin of life. However, it is conceivable that repeated passages through stellar systems or sustained internal heating from radioactive decay in larger bodies could provide the extended warm-wet conditions needed for life to emerge. Regardless of whether life forms on such objects, their role as carriers of prebiotic chemistry is well supported by the evidence from 3I Atlas. The combination of organic rich composition water-bearing minerals, magnetic shielding, and long-term stability during interstellar travel positions these bodies as natural distributors of the chemical building blocks for life across the galaxy. If such objects are common, and if they regularly deliver their contents to planets through impacts, atmospheric entry, or gravitational capture, then they could significantly accelerate the chemical evolution of planetary surfaces and atmospheres, providing a jumpstart to prebiotic chemistry that might otherwise require much longer timescales to develop through local processes alone, with the possibility of life formation and the mechanisms of molecular protection. Now explored, the next part will turn to the latest observational data, examining the strong sunward jet, the fading anti-sunward tail, and the intense filament patterns that indicate plasma influence, while also noting that overall activity is decreasing after perihelion, and that Earth's closest flyby on December 19th will mark the final peak opportunity for detailed observation before the object fades from view. These current observations will tie together all the physical, chemical, and magnetic themes developed across the previous parts, providing a real-time snapshot of an interstellar